Fusion is one of those subjects where the headlines tend to swing between miracle and failure. One week it is, limitless clean power is here. The next it is, fusion has been overhyped for decades. As of July 20th, 2026, neither story is right. Fusion has achieved real physics breakthroughs, but the full power plant problem is still unresolved. It is not solved, and it is not a failure. A good place to start is with a correction that changes almost every fusion headline. The phrase net energy is ambiguous. In fusion, different thresholds get mixed together as if they mean the same thing. They do not. There is plasma, or target gain, meaning the fusion fuel releases more energy than the energy directly delivered into the plasma or target. Then there is device-level gain, which asks about the machine more broadly. And then there is the hardest standard from a practical point of view, wall plug gain, or net electrical output, where the whole facility produces more electricity than it consumes. Many reports blur these levels. That is a basic source of confusion. The fuel cycle behind most serious reactor plans is also less futuristic than people often imagine. The main candidate remains deuterium-tritium fusion. Deuterium is relatively available. Tritium is the difficult partner. It is scarce, radioactive, and a real power plant would need to breed it during operation, typically from lithium. That is not a side issue. It is central. And that leads straight to the physical consequence at the heart of deuterium-tritium fusion. When those nuclei fuse, they produce an alpha particle and a 14.1 mega-electron-volt neutron. The alpha particle helps keep the plasma hot. The neutron is important because it carries useful energy outward, where it can in principle be turned into heat and then electricity. But the neutron is also a problem maker. It damages materials, embrittles structures, and activates components. In other words, the same reaction that gives deuterium-tritium fusion, its practical appeal also creates one of its biggest engineering burdens. That is why the blanket matters so much. In a deuterium-tritium reactor, the blanket is not just insulation and not just a heat collector. It has to do two jobs at once: absorb the neutron energy as heat and breed tritium from lithium. Without tritium breeding, there is no lasting deuterium-tritium power plant. This is one of the clearest dividing lines between a scientific fusion result and a commercial fusion system. So the commercial bottom line is very simple, and the certainty here is explicit. As of July 2026, none of the projects named here, NIF, ITER, or SPARC, has demonstrated wall plug gain or net electrical output. That said, there has been genuine progress, and the strongest recent evidence came from the U.S. National Ignition Facility, or NIF. On April 7, 2025, NIF produced 8.6 megajoules of fusion energy from 2.08 megajoules of laser energy delivered to the target. That was a real record and a real fuel physics breakthrough. It showed that under carefully created conditions, the target could give back much more fusion energy than the laser energy that actually hit it. But here again, the labels matter. NIF's target gain is not the same thing as system gain. A shot may use roughly 400 megajoules of electrical energy in flash lamps to deliver about 2 megajoules of ultraviolet laser energy to the target. So no overall electrical net gain is being claimed there. The result is important, but only if it is described honestly. NIF's chronology also matters because one criticism after the first ignition was that it might be a one-off. The first ignition occurred on December 5, 2022. Lawrence Livermore National Laboratory listed 11 ignitions through June 20, 2026. On the source basis of that official listing, the 2022 result does not appear to have been just a lucky outlier. Still, NIF is not a prototype power plant. It is inefficient, slow, and built for experiments, not industrial electricity production. A practical, inertial fusion plant would need very high repetition rates, cheap targets, precise target injection, durable optics, efficient drivers, and reliable heat-to-electric conversion. So the progress is real, but the gap between a famous shot in a lab and a power station on a grid remains enormous. The other major route is magnetic fusion, especially Tokamaks, the best-known approach. Tokamaks confine plasma with strong magnetic fields inside a donut-shaped chamber. The challenge is not just getting plasma hot enough. It is keeping it stable enough, long enough in a machine that can survive. In practice, plasmas remain unstable. Turbulence, coupling to the wall, and disruptions are serious risks, especially in large, high-power machines. That is not a public relations problem. It is a physics and engineering problem. This is where ITER enters the story. ITER is the large international tokamak under construction in France, and it is explicitly a research machine, not a power station. Under the 2024 baseline, the official plans say research operations in 2034, full magnetic energy in 2036, and deuterium-tritium operation in 2039. Headlines often frame ITER's delays politically, but the official reasons are technical. According to the official plans and reasons, the project needs more integrated commissioning time, additional heating, coil tests at 4 Kelvin, disruption mitigation, and a more robust startup approach. That source criticism matters. Political commentary may exist around any giant international project, but the narration here should separate headlines from the stated basis in the official documents. Outside the big public machines, private fusion companies have tried to move faster, and the strongest named example in this brief is Commonwealth Fusion Systems and its SPARC tokamak. In September 2025, SPARC had a full-scale toroidal field magnet power test independently validated in the U.S. Department of Energy Milestone Program. That is meaningful because high-field superconducting magnets are central to SPARC's concept. CFS also received a radioactive materials license in Massachusetts in 2024, another practical step beyond slides and promises. But the uncertainty needs to be preserved. In May 2026, CFS said SPARC is intended to begin operating in 2027. Those are company targets, not guaranteed forecasts. And SPARC's goal of Q greater than 1 refers to plasma physical gain, not grid electricity. So even if SPARC reaches its stated plasma target, that would not mean a fusion power plant is suddenly online. There is also a quieter but important track in fusion research, the stellarator. Unlike the tokamak, a stellarator aims for plasma confinement with a more complex magnetic geometry that may be better suited to steady-state operation. In 2025, the Max Planck Institute reported new best values from Wendelstein 7X, including triple product for long discharges and plasma durations above 30 seconds and above 43 seconds in certain power-related measures. That strengthens the stellarator's status as a serious steady-state plasma option. But again, the limit is as important as the achievement. Wendelstein 7-2X does not demonstrate tritium self-sufficiency, neutron-resistant materials, diverter lifetime, or economical remote maintenance. Those are not details to solve later. They are among the conditions for any real plant. And that brings us to, perhaps the strongest evidence against near-term commercialization. The U.S. Department of Energy Roadmap, published on June 9, 2026, explicitly identifies blankets and tritium fuel cycles, materials, diverters and heat exhaust, remote maintenance, and integrated test infrastructure as key challenges. That is striking because these are not minor optimizations around the edges. They are the industrial core of fusion power. In other words, fusion's hardest remaining problems are not only about making hotter plasmas or getting a better physics shot record, important as those are. The harder question is whether all the pieces can work together, repeatedly, economically, and safely, in one machine that breeds its own fuel, survives neutron damage, handles extreme heat, can be repaired remotely, and ultimately produces net electricity reliably enough to count as a power plant. So what should the balanced conclusion be in 2026? Plasma progress is real. NIF's repeated ignitions and its April 2025 record are real. ITER remains a serious scientific project, even with major delay. SPARC has credible hardware progress, while its schedule remains a company target rather than a guarantee. Wendelstein 7X has strengthened the case for the stellarator. None of that should be dismissed. But none of it removes the long road still ahead. The integrated power plant problem remains unsolved. Tritium breeding, blanket performance, neutron-tolerant materials, diverter survival, remote maintenance, and full system test infrastructure are still standing between breakthrough physics and commercial electricity. So the honest answer is less dramatic than the headlines. Fusion is neither done nor dead. It is advancing, unevenly, through a difficult transition from scientific triumphs to industrial reality. And as of July 20th, 2026, that road is still long. Subscribe, enable notifications, and suggest the next topic in the comments.